Hi, so today we are going to learn how to find those values for the critical values inside the margin of error in order to create our confidence intervals. The table I have up in front of us is one that you've seen before, but I'll just briefly reintroduce it. This is the standard normal table, which is used to find values for the z-score. And your possible z-scores are going to come from this first column and first row. And the main body of the table are your probabilities. So that's nothing that you've seen these before. What is going to be new is that the way we use this was you had a z-score and you found the probability. But now we're going to be working backwards because our goal is to get a z-score from a probability. So we're going to use the probability in order to find the corresponding z-score. And I'll get to that in a moment. But before I do, I want to introduce the new table for today, which is the T table. Again, this is also available on Canvas. It looks really similar, actually. You've got a bell-shaped symmetric diagram centered about 0. I don't believe that 0 is in your table, but it should be. And the other difference is that whereas the standard normal table gave probabilities to the left, the T table gives probabilities to the right. And so that's one initial difference. Something else that is different is the composition of the table itself. Now, the probabilities, according to this title up here, are just this line. That's it, just that top row. The first column has this DF notation, which is your degrees of freedom. And for now, those degrees of freedom are going to simply come from n minus 1, so 1 less than your sample size. And the body, which you can see many values are above 1, those aren't probabilities, those are your t-scores or t-values. All right, so let's figure out first, how do you find a critical value? The idea is the same, even though the tables are designed a little differently. So let's focus on this top left figure that I have here. The confidence intervals that I'm going to be teaching you all are all designed the same way. They're going to be two-tailed intervals, meaning that the confidence level is perfectly in the center of the distribution. And so I put 1 minus alpha right in the middle, symmetric about 0. So it is that unshaded area. But the total area has to be 1. So if there's 1 minus alpha in the middle, that means there's alpha not in the middle, or half of alpha on each side. And so that's where this alpha over 2 and this alpha over 2 came from. Now, the reason that I found those parts is because remember that the Z table gives you less than probabilities, and the T table gives you right-tailed or upper-tailed probabilities. And so I tend to use the left side for finding the critical value using the Z table, and the right side for finding the critical value using a T table. They're the same value, the same magnitude by symmetry, but that's kind of how I think. And so that process, again, is used regardless of which table you're going to be making use of. Let's get to some examples. And I want to focus on these 3 that I've kept on the screen. All right, so if we want a 95% confidence interval from you, and sigma is known, now that sigma is known signals us that we are going to be using the Z table. Right? And again, if you don't know why, look back at the last video. The Z table is used when sigma is known, because then your error is going to be Z star times sigma over root n. So if 95% is in the middle, that means 5% isn't half of that, or 2.5% is on each side. So I'm going to find 0.025 probability in the standard normal table and figure out what z-score corresponds to that 0.025. So as I look through, I see 0.025 right there. And if I go to the left, I see that is in the negative 1.9 row, and it's in the 0.06 column, which means that one of our z-scores is negative 1.96. But by symmetry, the other z-score must also be positive 1.96. So the critical values are plus and minus 1.96. Not too bad. You just need to remain focused with respect to which concept you're looking for. So let's look at a second one here. If we were doing a 90% confidence interval and sigma is still known, so it's still the standard normal table, 90% in the middle, 10% not in the middle, half that or 5% on each side. So I'm looking for 0.05. So we're looking for 0.05. Be sure not to add or subtract any zeros from this. 0.05 is not quite in the table. It is perfectly between these two numbers here. Literally, it's 0.0005 away from the left side and 0.0005 away from the right side. And so it's perfectly in between those two. That's important to keep in mind because this is the only time that I would expect that you interpolate. And what I mean by that is 0.0505 corresponds to negative 1.64, and 0.0495 corresponds to negative 1.65. And so if we were to go halfway in between, we would say negative 1.645 should be one of the critical values, and the other one will be the positive part. And that is exactly what I have found, which is pretty great. So plus or minus 1.645. The only time I'd want you to interpolate is if your probability is perfectly in between two z values or two probabilities. You can interpolate if it's closer to one or the other. I find students aren't necessarily good at that, but if you want to, it's a fine move to do. And so for our last example here, if we were doing a 99% confidence interval for P, same idea. Feel free to pause the video, try to do it yourself before listening to me talk on, but I'm going to continue. That means 1% not inside, half of that, or half a percent, 0.005 on each side. And when you look up 0.005, 0.005, this is another one that you will see is somewhere or perfectly between two values in the table. And so that corresponds to negative 2.575 plus or minus that. And we've got our answer of plus or minus 2.575. All right, so that's how you do it. What I'd like for you to do at this point is find the critical values corresponding to an 80%, a 75%, and a 94%, 4% confidence interval. Essentially fill in the last three parts of this table here. So pause the video, see if you could find the corresponding critical values, and when you're ready to check yourself, start back up. Okay, so let's come back and see how you guys were able to do. These are the values that you should have gotten or should be really close to, certainly within 0.01 of each of these. And so if you're doing an 80% confidence interval, that means 20% is not inside or 10% 0.1 on each side. And when you look for 0.1, I see is closest to 0.1003, which corresponds to plus or minus 1.28. And that's how I got my answer there. When you're doing 75% confidence interval, you should be looking at 0.125. And when you're doing a 94% confidence interval, you should be looking at 0.03. All right, so hopefully you're feeling fairly comfortable with finding critical values using the standard normal table. Again, you would be doing that if you're making an inference about mu when sigma is known. A little note here is how the confidence level impacts the value of the critical value. If you're having trouble seeing in this table, just go from smallest confidence level up and see how that affects your critical value. And what you should see is that it's increasing. So in other words, the more confident you want to be, the more error you should have, which is going to take you further to the left and further to the right from your point estimate. In other words, more confident, include more values in your interval. That's what's happening because your error is going to get bigger, and the bigger your error is, that means the wider your interval is going to be. So it's good to be aware of that interplay. Let's get to a couple other examples that I've got going on here. Well, if we want a 95% confidence interval from you when sigma is unknown in this case, so I'm focusing on the unknown part, and that you need to know the sample size. And in this case, I said n is 20, which means because sigma is unknown, we are going to be using the t-table. And if you're using the t-table, you need degrees of freedom, which means you need to know what n minus 1 is. And that's going to be 19 in this case. So again, the process is the same as what we did. 95% in the middle, 5% not, 2.5% on each side. So 0.025 is the probability that we're looking for. Make sure you're going to the right table. So the t-table, 0.025 is right here. And we're looking at 19 degrees of freedom, which is this row. So that's going to be in this column, which means we've got 2.093. By symmetry, that means we have plus or minus 2.093. And that should be the value that we got, which it is. So see if you could do this next one. What if you want a 90% confidence interval from you when sigma is unknown? Again, make sure you know which table you're going to. You've got a sample size of 11, which means your degrees of freedom is 10. And then see if you could find your critical value. You can pause. I'm going to wait about 10 seconds, and then I'll unhide it. So hopefully you're on the right track. Maybe many of you did actually get the value. What you're going to be doing with 90% in the middle, 10% outside, or 5% on one side is you're going to be looking at 0.05 in that column, 10 degrees of freedom row, and you should hopefully find 1.812. And of course, you want the positive and the negative side of that by symmetry. And that would be the critical value that you use. When you plug into the confidence interval formulas, you don't need to consider the negative side because you're plus and minusing. And so sticking with just the positive part is fine. It's gonna give you the correct lower and upper bounds. And so that's that. Now you've seen the formulas, you have the basic idea behind the motivation, why these exist, and you know how to get your critical values. So finally, in the next video, we're going to put it all together and find a number of confidence intervals.